I hope all of you are doing fine. In the last session, we have seen how unbalance is getting into the system, and we have as well understood how we can balance this system with the help of introduction of an external mass in the system to balance those inertia forces which are creating trouble, and we can make the system run smoothly. Out of which we have seen there are unbalances due to the pure rotating masses, due to the reciprocating masses, and the masses which are having combined motion. Out of which first we have dealt with, or we will be dealing with, the balancing of rotating masses, and we'll try to see how to get the graphical solution for balancing such systems, in which we will consider a first case, you can say, where several masses rotating on same plane. So there are several masses which are rotating on the same plane. One best example I can quote here is maybe a truck wheel, where it is having a tire, the wheel, and there are these various nut and bolts, the rim, maybe the tube inside it. Now you can imagine even the tire of the truck is quite heavy, so as if all these members, they are rotating on the same plane. So maybe in a way, if we just get an equivalence for this system, so maybe the center of mass of the tire is, say, concentrated at some point or at radius r1. There is the mass of the wheel, say m2, which is concentrated at some radius r2. The taken together masses of all the nut and bolts, maybe altogether equivalently they are, say, concentrated at some radius r3, and there is, let us say, the tube, let us include the tube as well in the system. It is concentrated, say mass is m at some radius r4, and which are having their own you can say phase distribution. So with respect to the vertical and horizontal, or maybe one of the references if I take, so maybe this as the reference, so let us say this is theta 1, or if I am taking this as the reference, so this is theta 1, say this is theta 2, and this is theta 3. So this is how they are distributed, and they are on the same plane. Now when they are on the same plane, that means I can place a balancing mass as well on the same plane. Now when these masses, when they are rotating at some angular velocity, so these masses are going to introduce a centrifugal force which will be acting radially outward. So say this is this F1, this is F2, this is F3, and this is F4. Sorry, this is F4, this is F3, and this is F2. So when these forces, they are radially acting outward, so there will be a resultant force out of these forces. So the resultant force will be acting somewhere else, and in that direction. Now as these are rotating, so that resultant force also will be changing its direction with respect to time, which will be creating this unbalance in the system. Now as these are rotating on the same plane, so I can I have a very great possibility of placing the balancing mass as well on the same plane, so there is no this moment issue comes into the picture, and I can balance this system. Now for this, if we go for the graphical solution, so as it is in the same plane, so I can go for the vector diagram. So these forces, this F1 will be M1 R1 omega square, F2 will be magnitudes will be M2 R2 omega 2 square omega square, M3 R3 omega square, F4 will be M4 R4 omega square. So if you see the system, omega is constant or omega is same for all these values, so we can neglect, we can consider the magnitude of that force to be equal to M1 R1. So if we write that, because we want the summation of all these forces which will be equal to the resultant force, and the balancing mass will be equal to that force, so that will be equal to the balancing force which will be mounted on the same shaft on which all these four masses are rotating, and whose omega will be the same as this. So when we are equating the magnitude of this, or the omega will be cancelled from the equation, so we can take these values as M1 R1, M2 R2, M3 R3. So if we go for the force diagram in this case, then so we will start with the, let us say this as the pole. Now so let us start with this. So this force is acting in this direction, so I can draw the vector for F1 of magnitude M1 R1 by selecting a proper scale. I can draw this vector. Let us say we know the magnitudes of all these M1, M2, M3, M4 and R1, R2, R3, R4, right? And I want to place, so I want to place a balancing mass at radius RB, and I have a limitation for this RB, because ultimately I can place this RB on the rim of the wheel. So maybe here, let us say I know this value of RB, and what I need to determine is the magnitude of this mass which is to be placed and its phase where I need to place it. Fine. So I can now find out these values. So by considering a suitable scale, so now I can draw these vectors, and all these forces, they will be on the same plane. So there is no much difficulty in drawing these vectors. So I can draw a vector parallel to F1. So let us say this is F1, which is M1 R1. So I call this as point 1. Then F2 is acting in this direction, radially outward from the pole. So I can draw a vector with a magnitude of M2 R2, say in this direction. So this is M2 R2. So let us say this is point 2. Then F3, which is acting in this direction, so parallel to this with this vector, say this is, so it is in this direction, so maybe in this direction I get this as M3 R3, and say F4, this force is acting in this direction, so maybe in this direction, so it is acting, say this is F4, so this is point 4, which is M4 R4. Now when this force polygon is drawn, the resultant will be given by, when we draw this vector joining the pole with the last vector, so this will be the resultant, right? Now we are trying to balance here that means we want a force which will be exactly opposite to this force, which is this R, the resultant force R. That means when we join, so the balancing force will be exactly opposite to it. So when we join this 4 with the pole, so this force will be the MBRB. So we have taken a suitable scale to draw these vectors. So we can now measure this vector length, convert it through with the help of our scale. Let us say it comes out to be some value L, right? So this MBRB is equal to L, and I can convert it through with the help of the scale, where here, as I have said, the RB or the radius of this balancing mass is known to me, so I can determine the magnitude of this balancing mass to be whatever that L, that means O4 length divided by RB. So whatever may be the unit, I can determine the magnitude of this balancing mass which is going to balance this system, as well as now I can place this vector, so I can draw the same vector. So this is the direction of the balancing force which is to be placed, or this is the balancing mass which is to be placed in the system. So I can draw a vector or draw a line parallel to this vector in my phase diagram, which will be representing the balancing mass at radius RB. So now if I have taken the reference as the mass 1, so this will be the angle which is the phase angle at which I need to place the balancing mass, and it will be balancing the entire system. So that is how in this case we can balance this system where several masses are rotating on the same plane. Now as all these masses are rotating, so if we see here, all these masses are rotating on the same plane, so there is no issue of this moment, because then the resultant force and their distance from the reference, whatever you consider, is going to be the same. So obviously the moments will be also get cancelled and the system will be completely balanced. So that is how we can we can get the graphical solution for balancing several masses rotating on a same plane. So now we will see the case where we can completely balance the rotating masses which are rotating at different planes. So now let's see where there are several masses rotating on different planes. So maybe there is a shaft, and on that shaft there are several masses mounted. Maybe a gear is mounted, a pulley is mounted, a flywheel is mounted, and they are separated by certain distance. So if we see its representation, so let us consider only 3 masses in this case, just to understand. So this is, say, mass 1 at R1, this is mass 2 at R2, and maybe this is mass 3 at radius R3. And when we are dealing with balancing of several masses, we prefer to place, let us say, 2 planes on which, so maybe I select, it can be any 2 planes, and usually these planes are near the bearings, but just to understand the case, so these are the two planes which I am selecting, where we will be placing the balancing masses. So say we want to place a balancing mass on this plane. Right now we don't know where, so maybe balancing mass L and balancing mass R, the left and the right, and let us say the radius of rotations for these are also known for us. We have to simply determine here the balancing masses ML and MR and their phase. So maybe, so say this is M1 at R1, this is say M2 R2 at R2, and this is M3 at radius R3, and we don't know where the phase of this ML and MR are going to lie. So with the help of graphical solution we will try to find out. So in this case again, we know that for dynamic balancing the summation of forces must be 0. Now as these masses are separated, so of course here only this condition is not going to balance the entire system. So as well we have to ensure that the summation of moments also comes out to be 0, so that the system is completely balanced. Now as we have seen in the earlier case, where we have drawn the force polygon and we could determine the resultant, and opposite to resultant we got the direction of the balancing mass or the force due to the balancing mass, which is going to balance the entire system. Now here if we are going to see in now our system, apart from these three masses we have to place two more masses, that is ML and MR at their respective radii. So now if I first go for, let us say, the force polygon, now if I want to go for the force, so the force due to M1 will be acting in this direction, the force due to M3 will be acting in this direction, and the force due to M2 is going to act in this direction. As well as the forces MR and ML, they are also going to act radially outward. Now if I go for the force polygon, so their phases with respect to say the R1, say R1 is the reference for determining the phase, so theta 1 and theta 2, let us say, we know. Now I can draw the vector for force of F1, which will be in this direction, vector for force F2 in this direction, so this is F1, this is F2, and vector force for force F3 is in this direction. But here the forces due to MR and ML both are unknown to me, so I am not in a position to draw these two vectors right now. So as if there are two unknowns in a single equation, so I am unable to find out the solution for this. That means force polygon is not going to give me the solution right now in this case. So in that case as well, we know in this case we as well know that the sum of the moments also must be 0. Now then, that means to determine the moment due to all these forces, I need to select a reference plane, right, about which the moment of these forces can be calculated, and the vector for the moment due to these forces can be drawn. So instead of going for the force polygon first, we will go for the couple polygon or the moment polygon, which is going to give us partial, the solution, and then force polygon can be completed. So here now, first we will have to select one of the balancing unknown mass plane to be one of the reference, so that the moment due to that unknown mass is 0. So here I will select this, the left plane, as the reference plane. Now I can as well select the reference as the right plane and go for the solution. But here we need to understand one thing as well. Now when we are, let us say, I am considering the reference plane, let us say, as the MR. So now for this I as well need to know, or we will be supplied by the distance of all these planes, or the separations of all these planes. Let us say this is L1, this is L2, this is L, and this is L3. So the moment due to this force M1 will be, if this is the reference plane, it will be M1 into L1. For the force F2, that will be F2 into L2. This will be the moment due to this force, and the moment due to this mass M3 will be F3 into L3, where F is M into R. And the moment due to this balancing mass MR will be equal to FR into L. So if these L1, L2, L and L3 are known, so even I can determine the magnitudes of these couple or the moments. Now let us see what will happen if I select this MR as the reference plane. Now we know that the force due to, say, this M3 is in this direction. So F3 is M3 R3. Now by applying the right hand screw rule or right hand thumb rule, we know that the moment vector will be perpendicular, it will be perpendicular to the force vector, or it is perpendicular to the plane of rotation, as we know, and the plane of the force is on the plane of rotation. That means the moment due to this force will be perpendicular to the plane of rotation. That means this vector or the couple vector will be perpendicular to the force vector. So if this is the case, then say this is the couple vector, which is M3 R3 L3, and it will be perpendicular to this force. Now with reference to what? With reference to the MR we have considered, right? So not L3, in that case it will be this distance, whatever, say, let us say this is A, so it will be this value A, and the distance of, let us say, the R2 is some value B. Now this mass is opposite to that plane and he is rotating in the same plane. So when it is opposite to that reference plane, in that case the couple vector for R2 will be in the opposite direction too. So this will be M2 R2 B. So we can see that when the forces are on the same side, so here I'll take this distance, if this is the reference, say this is A, so this will be minus B, isn't it? It is opposite to the reference plane. That means this magnitude is of the couple is opposite to this couple vector. So that means if the four masses are on the same side of the reference plane, then the direction of their couple vectors will be also in the same side. And as we know that the couple vectors will be perpendicular, so perpendicular to the force vectors. So when we are drawing the couple vectors, we need to understand what is the force vector, and then perpendicular to it we will draw the force vector. So that the couple vector. That means for every couple vector we will see the direction of the force vector, and perpendicular to that we are going to draw the couple vector. Now instead of doing so every time for a couple vector, we can simply draw the couple vectors parallel to the force vectors and simply rotate the entire couple polygon by 90 degrees. So it is not going to change the phase differences, as a matter of fact. So that means we can go for the couples which we are drawing that will be parallel to the force vectors. Only thing we have to keep in mind that the direction of the couple vectors will be same if they are lying on the same side of the reference plane. If they are at the other side of the plane, that means if you take the reference plane as MR and say in this we state that this is positive direction for the couple, then the couple due to when we are drawing the couple vector, so the couple due to the M3 will be same as the direction of the force, whereas when we are drawing the couple vectors for M1 and M2, they will be parallel to F1 and F2, but they will be in the opposite direction to this force vectors. So that is how we will be interpret these vectors when we are drawing the couple vectors. Now, as if now in this, just for understanding how we are getting the solution, I consider the left reference plane, left plane of the balancing mass plane to be the reference plane. So all these masses, they are on the same side of the reference plane. So I consider this as the positive side, right? So that means when we are drawing the couple vectors, we will consider the direction of the couple vectors also to be the same as the direction of the force vectors. So what is the force? Force I can write M into R, and the couple will be M into R into the L. L is the distance of the plane of rotation from the reference plane where balancing mass is placed. So now I can go for the couple polygon. We will select a suitable scale. So we can select a suitable scale. So maybe 1 centimeter or 1 mm will be equal to MRL. So we can. So now I select the pole for couple vector. Now we have taken this as the reference. So couple due to mass L will be 0. So now if I see this equation here, the couple due to M1, R1, L1 will be parallel to the phase. So I can draw this vector parallel to F1, which is M1, R1, L1. So I get this as first. Then it is 2. So M2. So this is M2, R2, L2. Then right now I don't know about the vector MR. So M3 is in this direction. So parallel to this from here. So I can draw, say I get this to be as the third point. So this is M3, R3, L3. So now I can say this is the resultant couple. So opposite to that, that means if we reach back to the pole, so when we reach back to this pole, so this is MR, RR, LR. Now here ML, RL, LL, ML will be 0 for this, so there is no, so there is this equation, one equation with one unknown. So we can now measure this value, whatever this value, this will be equal to O3, and we can determine the mass as the length O3 divided by R L3. So we can find out the magnitude for this mass, which is to be placed at the right plane for balancing the system. So I have determined this value, so I can draw this vector, so match, I can draw this mass parallel to this vector on the phase diagram. So here I get the phase of MR. So now once this couple vector is done, when it is finished, we have determined the one of the balancing masses which is to be placed at the right plane. Now we can go for the force polygon. Earlier we have seen in the force polygon we had two unknowns, the ML and the MR. Now we have, with the help of the couple polygon, we have determined the MR value. So now we will go for the force polygon. So again we can take a suitable scale, as 1 centimeter will be whatever unit it comes out to be. So now we take the pole. So again force M1 is in this direction. So I get this as M1R1. Then M2 is in this direction. So this is, say, M2R2. Then M3R3. So this is M3R3, and then we have determined M4. So the force due to this will be in this direction. So this parallel to this one, so maybe somewhere here. I get this as MRRR, and so this is 1, 2, 3, this is 4. So maybe now when we come back to the pole, so this vector is MLRL. So now MLRL is equal to the length O4. So we can convert it to the scale as RL maybe is known to us. So this is by RL. So again we can determine ML, and the direction of this ML is in this, so parallel to this. So maybe in this direction we get the mass ML at the radius RL. Thus both these balancing masses with their phases. Now if I take the reference as M1, then this is the angle or the phase angle of the right plane which is to be placed on this plane, and this is